Hi everyone. Welcome to the second session of the Bitcoin Kernel Club. In the first session, we just looked at what is Bitcoin kernel or what is libbitcoin kernel. Both are the same name, and what it does, why is their requirement, and everything. And also, we have looked into the C API or basically the header file, and also the error handling on some stuff like that. So in this session, we'll just do some more hands-on, but before that, I have a bunch of uh, topics that we need to discuss before we get we do the hands-on with the API. The first one is first of all we'll review what Bitcoin kernel is, and then we'll be looking at what is consensus verification and what is full verification, or basically types of verification in Bitcoin, or basically in Bitcoin nodes or in Bitcoin core. And also we'll be looking at what is context-free validation or what is full validation. Both are different, and what are some of the use cases of context-free and what are some of the use cases of full validation. Also, we'll be looking at the memory management. Memory management basically is the reason why we have different language bindings, and that's the reason why we have the API in the C language. Let us review or basically go a bit about what Bitcoin kernel or libbitcoin kernel is. So in the previous session, we just knew that Bitcoin core or other Bitcoin nodes have a bunch of subsystem, or basically collection of subsystem, which makes the nodes the Bitcoin nodes. So we have P2P, we have GUI, we have wallet, we have consensus engine, we have mempool, and we have RPCs. So every subsystem has its own use cases. So the heart of it all is the consensus engine, and why I referred the consensus engine as the heart of it all, though, because it tracks of all the blocks, it manages the UTXO set, and you can find that in your in your system when you run Bitcoin node. Then you will have all these files, the blocks, this blocks folder and this change state folder. These are actually the blocks and the UTXO set. Change state is actually the UTXO set, and the blocks is actually the collection of blockchain or the block that has been mined, or basically the blocks that you have got from your peers. So basically consensus engine is actually the code or the logic which defines what Bitcoin is, what a Bitcoin blockchain is, because it is the fundamental logic or validation logic which defines what a block should be or what all transaction should be. That's the main idea, and that's the consensus engine. And in a distributed system where like Bitcoin, we have a bunch of folks running Bitcoin nodes. It doesn't matter if it's prune or if it is full node or if it's SPV nodes. So because not SPV but full node and a prune nodes, because every full node and prune node, they actually validate the blocks and the transactions that has been received from their peers or the peers that they are connected to. So like we should have a uniform consensus engine, or basically a same or basically uniform validation logic, so that everybody is in sync. So if this person is running a Bitcoin node that has different consensus engine, it's like somebody is running BTCD or different consensus engine, not actually different, but maybe they have written the consensus engine by looking at the Bitcoin standard or the white paper, but ignoring all the language specifics, bugs or quirks. So what happens is, if they have built a consensus engine is Golang or in Java, and most of the nodes in Bitcoin, they are actually running the consensus engine in C++, not C but C++ basically. So what happens is, there might be some bug in Java. For example, parsing an integer or basically JSON in Java might be a different than parsing a JSON or integer or data in C++ might be different. So most of the nodes are running C++. So what happens is then the Java 1 or the consensus engine that has been written in Java will not be in the sync will not be in sync with other nodes because it parses differently, and what most of them are using the C++, they are parsing differently. So that's the main idea. So everybody should have a uniform consensus engine or validation logic. So that's the requirement. And we have seen a lot of this problems in history. There was a consensus bug and in BTCD. So BTCD, not sure, they didn't disclose, that's why it's not disclosure. BTCD is written in Golang, so because of that there was a consensus bug. So anybody running version 24.2 or 0.24.2 BTCD are not in the Bitcoin network or basically in consensus with all the Bitcoin nodes running. Similar goes for the libbitcoin. Libbitcoin is another project which does all the full Bitcoin node you can create. This libbitcoin is actually written in C++, and the Bitcoin core or Bitcoin nodes, they have the consensus engine in C++. Still libbitcoin has a consensus bug or basically a consensus failure bug. So as you can see, having a same language, programming language for both of the consensus engine might be differ in the consensus engine. So that's the main requirement. That's the main problem, or basically the reason why we have Bitcoin kernel, so that we have a uniform consensus engine. So if you have non-uniform RPCs or GUI or wallet, it doesn't matter. But if you are having different consensus engine or non-uniform consensus engine, then we'll be having some hard forks or a bunch of folks running different Bitcoin nodes and a bunch of folks running different Bitcoin nodes. So that's when the hard forks happen. And also we have talked about code entanglement. As you can see in the Bitcoin core, we have uh, code entanglement, which means that consensus engine is not actually written in a single file or in a single folder. It is actually distributed in all other subsystems. Like we have a consensus engine is RPC as well. So RPC code as well, we have a consensus, some validation logic written in RPC's code, some validation logic written in mempool, GUI, P2P. We have a lot of in P2P and in wallet as well. So extracting out the consensus engine from all of this subsystem is actually one of the goals of this Bitcoin kernel. So when we extract out all the consensus logic from the other subsystem, then the consensus engine, what happens is now we can reuse this validation logic with the library. Library will actually expose this consensus engine and anybody can use this consensus engine. So first step, or basically a incremental step, is to make a library as well from the scratch, and then we also want to entangle the code validation logic from other parts of the Bitcoin core basically. And also experimenters, if they want to experiment, if they want to re-implement mempool or basically get rid of mempool, what UTXO does, or Swift Sync, what they do, they don't require mempool for the bridge nodes. And similar way, if you want to implement your own peer-to-peer network protocol, then you can just implement that by using the consensus engine. If you want to replace the RPCs with the greatest and the most efficient gRPC, and if you don't want graphical user interface, you want the terminal user interface, you can use that. And wallet is a different rabbit hole. And also similar goes for the Rust. Maybe somebody wants to create a crate for different subsystem, like P2P wallet. For the RPCs, they can use CAPN and CAPN protocol, and for the Bitcoin, for the mempool part, they can implement their own Bitcoin mempool that will have different mempool logic, and also context for UI, different UI for their own node, or as per the requirement of the community. So these are the challenges faced. They can have their feature get into Bitcoin Core, but Bitcoin Core doesn't want to bloat the code base, or basically, doesn't want to add more features because they actually bloat the code base, and there might not be enough reviews for the PR for the feature that you have implemented or basically proposed in the Bitcoin Core. So that is one of the challenges. The another one is fork. Uh, if somebody wants to, if the first one is actually PR review, if that doesn't work, then what they do is, what they can do is they can just fork the Bitcoin Core. This is not network fork. This is actually a code base fork. You can fork from GitHub and you can do whatever features you want, and then there is a problem is that you have to trust that author, or basically that community, for maintaining that Bitcoin fork, and then implement the whole consensus engine in different languages, or different in different way. So we have seen that happening with libbitcoin and the BTCD. That is another challenges. So we are faced with three challenges, and this is actually an big reason why Bitcoin kernel was built, so that now you don't have to do any of this. You don't have to face any of these challenges. You have the consensus engine. Now you can implement your own, whatever you want, but you have to use that consensus engine. Now you will be staying in Bitcoin network, and you can experiment or basically build anything you want. So basically we are lowering the cost of experimentation. There was a prior effort. We have already seen that early Bitcoin consensus in version 0.10 back in 2016 that only supported script verification. It lacked UTXO set management, block tree management, and block validation. Block validation is the most important part, and it was lacking that. So that was actually incomplete, and yeah, and but there was a lot of effort in completing this Bitcoin consensus, but it wasn't able to complete because it had different goals. They were planning to build the Bitcoin consensus from, they want to build from, like, complete the whole library from scratch. And so that's why Bitcoin kernel or Bitcoin kernel, they had an incremental approach. It's like build something that can be, worked, basic one, and then we'll just improve that. So that was the difference between this library and the Bitcoin kernel. So yeah, we have seen that we will be using existing classes, and then expose that through the API, and then refine that API as per the requirements. So there is a there are lots of PR, including mine, which added some like support. For example, right now we don't have support for block header. So if the PR gets merged, I've opened one, and if it gets merged, then we'll have support for block header as well. You can create a block header. You can pass your block hash. Yeah, you can pass your block hash, or basically raw block data, and from that it will create a block header API, not API but object, and from that you can validate whether the block header is correct or not. You can do consensus checks, and you can also do uh, full check as well. And this was the PR which introduced the initial kernel library, or basically C header API 30595, and it had lots of problems, but this was actually the basic or the base version of the library. And So, and these are all the language bindings currently available. We have in Rust, we have in Python, we have in Java, and we have in Go. We also have in .NET, and we also have in JavaScript. And some of the use cases are, you can make your, you can do some academic research on the blocks data, uh, whether that all the data you have is actually consensus correct or not. You can do that with the kernel client or read-only kernel clients. And external indexers like silent payments, CoinSwap, they might require libbitcoin kernel for validation works, and also different clients, they don't require mempool web that is Floresta or UTX. So Floresta uses UTX protocol, and Swift Sync or Bitcoin J, etc., and also personal projects. If you have any personal projects that might require the consensus engine, then you can use this library. These are all the future improvements. Sans I version of the API on isolated kernel repo. Isolated kernel repo is basically we have an isolated GitHub repo, or any other GitLab or something like that. We'll have that repo, and that repo will just contain the consensus engine, including this library. So that is the main idea. This might take a lot of time. And also, if you want your own mempool policy, then you can plug that mempool policy. That is the future improvements. And context minimal validation, it's like only the consensus checks, not the full validation checks. So this was it about the Bitcoin kernel. Now, the next topic that I want to discuss is actually types of consensus verification. So basically, we have two types of consensus verification. This is actually not defined by any Bitcoin white paper or something like that, but this is actually followed by most of the Bitcoin nodes running in the Bitcoin network. Okay, so consensus verification. The first one is actually partial verification. So what actually is partial verification? Think of it like you have a transaction, you have a block. Okay, so you can validate a transaction whether the transaction contains whether that script pub key matches with the locking, or basically the unlocking script, or basically the script sig, whether that matches. That is actually consensus checks. And or basically the partial verification. And also similar goes for the block, whether that block has whether that blocks has some Coinbase transaction, whether that blocks has the transaction hash or something like that, whether that block header. You can do all that partial verification. And what does full validation means is that including the partial verification. Now suppose you want to fully validate a transaction, so you can you have to look whether that previously spent transaction of this transaction exist, or basically is mined in the Bitcoin network or in the blockchain or not. So you have to look that. So for that you need the whole blockchain state. For example, if a transaction has been mined in block number 83, now the transaction is to you or to us, and suppose we want to spend the transaction. You have 3 Bitcoin and you want to spend the transaction. So for that you will need the previous out, or basically the spent outputs. So for that you will need the whole blockchain state. So in that case, if we have done that verification as well, whether that transaction or basically the previous output exists in the blockchain or not, basically it is mined or not, if we have done that validation as well, then that is considered as the full validation. So full validation also include all the partial verification. Partial verification is all performing all the consensus checks. Okay, and then similar goes for the block, whether that block whether the hash of the block is lesser than the the previous one or with the difficulty. So we need to check that. For that, we need the whole blockchain state. So the drawback with the full validation, or basically extra requirement, is that you'll need all the blockchain state, or basically the chain state data. So also, in a transaction, if you want to validate a transaction, then it will also look into the chain state data. Chain state data is actually the UTXO set, so it will also look into the UTXOs, or basically the mempool, whether it contains the UTXO or not for that transaction. So for that, we need all the block and the chain state, or basically the UTXO data. So you need the whole blockchain state right from the Genesis block. So that is the full validation. That is the difference between the full validation and the partial verification. So the thing is, if a transaction or a block passes the partial verification or consensus checks, then it doesn't mean that it is fully valid block or transaction, because it hasn't passed the full validation checks. So full validation checks is actually necessary in terms of the Bitcoin. So passing a partial verification doesn't mean it is fully valid. So that's the difference between full validation and partial verification. In partial verification, we don't require any blocks or chain state data. It just needs to pass all the consensus check, or the valid, or the the code, or the C++ code. It needs to pass the validation logic. So that's the difference between partial verification and full validation. Now let us look into the third topic that I want to discuss. It's actually what is context-free validation, what is full validation, that we have already discussed. This is actually the difference. This partial verification is actually context-free, and full validation is actually also known as contextual validation or full validation. And what does context means? Context means you need a context, and it means that you need the whole blocks data or the chain state data. That is meant by the context. So if somebody says what is context, then it means that you need to have some context to validate the block or transaction. What does context means? You need the whole blockchain state and the mempool, or basically the UTXO data or the chain state data. So that is the meaning of the context. And what I want to discuss is let us look how is context free validation works, and how is full validation work through the API, by using the API. So let us create a mix cell. So if you see here, this is actually context free validation. So we don't require any block or the chain state data for now, because we are just doing a partial verification, or also known as context free validation. So we have taken a transaction, that is a tap2 transaction, and this is the hexadecimal array of the tap2 transaction, and then we also have a script pub key, and this is actually a hexadecimal representation of the script pub key. So what we'll do is we'll actually match whether this script pub key is yep. Any question? whether that script or pub key matches this transaction or not. Okay. So we have the transaction raw transaction data. We have the script pub key data. Now what we'll do is we'll actually create a transaction object. But before that, I just want to explain you the memory management part. Okay. So what happens is think of this like native or C memory, because we have our C code written in, we have our library written in C language, and then think of this as the bindings, like Rust or Java or C++, something like that. Now, since our library is written in C and our bindings is written in C++, so what happens is whenever whenever we create an object, or basically whenever we create a transaction object, so we need to allocate some memory in the heap or in the stack of our system. Okay. So what happens is if you create a transaction object by taking this transaction data, because we have taken this transaction array, or basically the raw transaction, and we are creating a transaction object of type BTCK transaction. This is defined in the header file. See, we are creating the BTCK transaction is defined in the header file. That is actually your data structure, or basically the type of the data. Okay, and name of the data type is transaction, and we are creating a transaction object, or you can say we are allocating this transaction data in the memory or in the disk, in the stack or the heap. Okay, and we are passing this transaction raw transaction data, and we are passing the size of this whole transaction data. Now what this will do is this will actually create uh, this will actually create or basically allocate some memory for raw transaction data. So if the transaction data has allocated some memory, it will stay in this C memory. Okay, I'll just write it down. BTCK transaction. So in short, I've written like this. So we have created a type that is BTCK transaction by using this BTCK transaction create method. Now that will be stored in this native, or basically the C memory, and both of them are in the same system, but that the memory is differentiated. So we've created a transaction, or we have created this data type or data in the C memory, and then now if you try to access this transaction data from the bindings or in your own language, you can't access. You can't access.
They don't please your back. Time.
Yeah. So you can't access this transaction data from your own programming language, because this is in C memory, and the other language they can't access this one directly. So for that case, we have so when we try to allocate memory in the system, so we need to also handle whether that transaction data that has been created by this method or not. There might be some error while allocating some memory. For that, it needs to handle. So that's why we have a check here. And if 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 the memory allocation fails, then this method will return actually will return it will return whether if the memory allocation succeeded, it will return the transaction pointer, or basically a pointer to the transaction, or if it failed, then it will return null. So we'll handle that. So if it is null, then we'll just print whether that transaction creation has been failed. Similar way, we are creating a script pub key as well, because this script pub key is actually in the raw form, but we need the script pub key in the BTCK script pub key type, because everybody should have a uniform data structure. So for that case, we need to have a BTCK script pub key type, and for that we need to allocate some memory in the system, in the stack or the heap. And for that we have a method called btcget we have a method called btcget script pub key create, and again that takes script raw pointer, or basically the array of script hexadecimal data and size of the script. We'll handle the error as well similar way. For this part and this part, we'll just see later why we need const transaction data instead of mutable transaction. So if you see here, we have a BTCK transaction data type. This is not actually a const, this is a mutable one. So you can change this transaction data to other as well, but we are making the mutable, we are taking from the mutable, we are taking to immutable, we are taking a const. Okay, we are just making from mutable to immutable. So that's the idea, and we require that when we are validating a script okay with respect to the transaction. Next we have the amount, the value this transaction contains, or basically the value that this transaction should contain. And then we have a transaction output as well, or basically spent outputs. And for that we need to create we need to allocate the spent outputs in the memory, basically in the system. So for that we have this function which will allocate the spent outputs data, and then if it failed, it will return null. So you can see here it returns the transaction output, or basically null on error. So this will return the transaction output or null while if there is some error while creating the or allocating the memory for this spent outputs. Again, we are actually taking the transaction output. We are making this transaction output to be const, because we want that spent outputs to be immutable. We don't want it to be mutable. Okay. And next we are actually creating a spent outputs array. So if you've seen, a transaction might contain multiple spent outputs, there might be lots of inputs and there might be lots of outputs. So for that case, we need to have a spent outputs array, or basically a collection of spent outputs. So currently we only have one spent outputs. So suppose you have a transaction that you want to validate that contains multiple spent outputs. So you can again create something like this. Something like this. You can create another spent outputs, and that should be here. So we are just creating a spent outputs array. So since this transaction only contains one spent output, so I'll just move this one. And then The next is the pre-computed data. So if you're familiar with pre-computed transaction data, it's like uh, when a transaction is created. So while its creation, we do all the pre-computed part. Pre-computed in the sense like it already creates a transaction ID and a bunch of stuff, but mostly I remember it creates the transaction ID automatically in the compile time. So that makes the transaction fetching or basically parsing very efficient. This is in Bitcoin Core. I'm not sure if this pre-computed is available in other Bitcoin clients. Not sure if it's available in BTCD or Bitcoin, but it's available in Bitcoin Core because this makes the transaction fetching and doing all the computation with the transaction very fast. And the next is, so again, we need to allocate the pre-computed transaction data in the memory. And for that, we have this function you can create. And then we need the const reference to the pre-computed data. And then we also have a script verify status. For example, if you see in this PTCK script pubkey verify, then it just returns 1 and 0. 1 means the script verification was successful and 0 means the script verification wasn't successful. But we need a robust error why this script verification failed. I mean, why why this transaction verification was failed. There might be some input incorrect, or we have lots of script enums. There might be lots of different reason why this script verification was failed with respect to this transaction. So we need that 0 and 1 is not actually a robust error. For that case, we need to pass this we need to pass this status, and status is actually we are creating a BTCK script verify status, and this is also a data structure that is exposed in the library. So it has a bunch of enums, whether that script verification was successful, whether that script verification was error, or it has invalid flags combination, whether that script verification was error while spending the outputs. So there are lots of script verification error, but we have only exposed this three, and likewise, I already said we want to create a incremental approach. So if there is a requirement for exposing all the script verification, I actually have a branch which exposed all the script verification. Let's show you that. Yeah. So if there is, let me just open this one. So if the script verification failed with respect of the transaction, then we can have a lot of script error, something like this: BTCK script error, unknown error, evaluate false, overwritten, why this script size, or we have a lot of, I guess there is 30 to 40 script errors, like why this script verification failed. So currently we are only exposing 3, but if there is some requirement by the community that we need more, then we can just expose this. And for that, we are just allocating status. We're creating a variable named BTCK script verify status, and then the variable type or basically contains this script verify status k, and it contains the value 0. So we are not storing this, we are actually storing 0. And the next one, if we define this status as script verify error invalid flags combination, and it will contain the value 1. It will not contain this value, it will contain 1. It will not contain string, it will contain 1. So we are actually dealing with the number instead of the string. And then we have created the status. Now the interesting part comes. We will supply all the data that we have created. We'll supply that, and we'll supply to this function. We'll pass to this function script pub key verify. We'll just pass the script pub key that we have created, and mind that script pub key we have underscore here, so that means this is the const. This is not actually the mutable one, this is actually the const one. So if you try to pass here the mutable one, then this doesn't work, or basically it will actually give the error while we compile it. So we need to pass the const reference or the const value. So you can see here we need the const of the btck script pub key. The data type is btck script pub key, but we need the immutable one. And the amount, it's already in 64 integer, signed integer. And then we have the transaction. Similar for the transaction, we need the const btck transaction type, basically the immutable transaction type, not the mutable one. Similar goes for pre-computed, we need immutable pre-computed data. And why do we need, why are we actually passing the immutable data here? Because we don't want that you have created or basically you have allocated a memory. You don't want this function to actually modify the value, so we don't want that. And also in C, what happens is when you pass a non-const reference or basically the mutable data, so when you pass a mutable data, if you pass through reference, now if you have passed that value, if it's valid, now you can mutate or basically you can change that value. So if the value is changed, and the script verification won't pass. So that's the main idea. So we don't want to change the value while it's validating, but we can change before the validation and after the validation. So we don't want to change while the validation works. That's why we don't want to pass the immutable data. We just, or basically the mutable data, we need to pass the immutable one. And we are supplying what type of verification we want. We want what type of verification we want. If you want that the verification to be, none, like it's like no verification, then we can just pass this data type. Or if you want to check whether that verification to be P2SH or dir signature, null dummy, you have lots of script verification flags that you can pass. So we are passing all, that means we want to check all the flags. Okay, so all is actually the OR of all the previous value. So if you see here, we are not actually passing this script verification flags none, we are actually passing the value 0. And similar goes for the next one. We are doing left shift, that is 2, or basically 2 to the power how much left shift you are doing. And then we are doing the left shift by 2, and then after that we are doing the left shift by 4. So we are all doing this in bits. And why we are doing in bits? Because bits is actually faster in computer instead of just passing a raw integer. And then we are passing a reference to status. Mind that we could have passed like this, but we are actually passing like this because we want if there is a verification failure, then we want the status to be changed. and if you pass through ampersand, what happens is we are actually passing the memory. We're not actually, if we do like this, then we are actually creating a copy of this status and we're passing that status. So we don't want that. We don't want to pass a copy of this status, but we want to pass this status as well. Because if there is verification failed, then we can get this status, or this status value changes from something like, you know, something like this value or something, or this value. So we want to capture that. So this is actually the reason why we are passing status, or basically the reference to the status, not actually a copy of the status. So after that, you've seen that in C we have allocated a lots of memory. So if you don't destroy it, then C doesn't destroy, because it's not a garbage collection language like Java or Golang. So you don't need to destroy the memory in Java and Golang, but in C you have to destroy whatever you have allocated. So for that, we'll just destroy all the transaction output, and we need to destroy script pub key, the transaction, and then transaction, the data, the pre-computed, all of that. So after that, we have seen that the result value has been captured. If it is 0, that means the script verification failed. If it is 1, that means the script verification was succeeded. Now we could have created lots of if else statement here as well. If that script verification was failed, then we can just check whether what is the status of this script verification. So we could have created an if else statement. If the script verification gives this value, that means uh, the flags were combined in an invalid way. So the script has invalid way of combining the flags. Or if we got this value, that means the taproot flag was not valid, or it wasn't provided. Spent outputs have to be provided. So we could get the error value through the status, through the status. So if we don't pass here through reference, then what happens is the status never changes, never updates to why it failed or why it succeeded. For that case, we need to pass the reference. So this is actually the context-free validation. So if you see here, we didn't need the whole blockchain state or the whole chain state or UTX or mempool state. So this is just the partial verification. We're not doing full verification. We are just doing partial verification. So if you just try to run, it does the build, make run. So if you see here, the script verification succeeded. Now, if I want to change something like this, then this should definitely fail. Script verification failed. Okay. So this was it about the partial verification. Now we'll actually look the full verification. So I've already created some code. Let us go to this main function method. If you see here, to create a context, we can use this BTCK context options type, and then you can create a constant object, a context object, and then you can also create a notification callback as well. So what does notification callback does? It's actually when there is a new block, or basically when you got a new block from your peer-to-peer subsystem, then this will notify. So whether that new block was uh, was received, whether that what is the progress, or basically the verification of the new block, and what is the block tip when that verification has been called succeeded, or the new block verification has succeeded. You can check all of this from this notification interface callbacks. And you can also set the context options. It's like context, we have already discussed what context is. Context is actually having a full blockchain data, or basically the UTXO data, or set, or mempool data. So now you can create context options, set notification. So it's like when the context is created, you can set the notification callback. This is the notification callback, which handles all the block tip and stuff like that. Whatever notification you can get from your peer-to-peer subsystem. So that's the main idea why notification interface callbacks was made. And then we also have a validation interface callbacks. It's like when when a new block is received, and what is the validation status of the new block, or basically the block that has been received from the peer-to-peer subsystem. So if you want to check whether that block has passed all the consensus checks, or full check, not consensus check, full check, whether it has passed the full check. If it has passed the full check, then it will return that block has been connected. If it didn't pass the full check, then it will just return block connected false, or block disconnected, and something like that. So notification interface also handles when there is a chain reorganization, when there is two chains, or basically two miners are competing for a block. Then you can have a notification whether you have got a two chain, and which one was disconnected, which one was connected. So all that is handled by the notification interface callback, and you need to pass this value to this context options, because if you don't pass, then context options thinks that you don't need the notification callbacks. Similar goes for the validation interface. If you don't need any validation interface, then you can just if you don't want the validation interface callbacks, then you can set it to null. Now we need to create a chain state, or the chain parameters. It's like which chain you want to use. You want to use mainnet, regtest, testnet, or signet. So you need to create that as well, chain parameters, and you need to pass that chain parameters to the context. So here we are just till here we were just creating the context options. We haven't created context. What is the difference between context and context options? Is that context options, it's like creating options for the context. Okay, like you want this, you want that. You are actually customizing the context. You're not actually creating. First of all, you are customizing whatever requirements you have, and then if all of them has been completed, all your requirements has been completed, now you will create a context. Because after you create a context, if you want to change or customize all of that, then that's a very expensive move or step. So to reduce that, first of all, we are creating what all options you want for the context, and then we are with that options, you will create a context. So now we are creating a context, and context in the C library, or basically in the C API or Bitcoin kernel API, has the data type BTCK context. Okay, that is actually a data type, and the data name is actually context. You can keep whatever you want. Lots of people do like this, CTX, but you can, I'll just go with context. And to create a context, you need to use this method BTCK context create, and pass the context options and handle the errors. Okay, Now, if you see here, we have created context, we have created change state. Now you need to deallocate the memory, because while creating context options, we have created memory to customize that. So for that reason, we need to deallocate memory, because we've already allocated memory for context. Now we don't need the memory for the context option and the change state parameters, like test signet, mainnet, or testnet. And we need to also specify the context state, or basically the data where it contains. If you have a blocks or data directory, you need to mention that, because I've already said that when doing full validation, you need the whole blockchain state or the mempool state. For that reason, you need to have a data directory and the blocks directory, which should contain all the blocks data and the change state data. So now we have already created the context. Now we need to create the change state. Okay. Basically the block data. Now we need to create the change state. So for that, again, we have a change state manager options. We have options. What options you'd like to have. So here we are passing the context that we have already created here, and then we'll pass the data directory, the length of the data directory, the blocks, and the length of the blocks directory. If this memory allocation fails, we'll handle this. Then we'll create a chain man, or basically change state manager. And what change state manager does is actually a data type that does all the full validation. If we look into the header file, then opaque data structure for holding a change state manager. So if you read this one, the change state manager is a central object for doing all the validation tasks as well as retrieving data from the chain. Internally, it is a complex data structure with diverse functionality. So change state manager is actually defined in Bitcoin Core or in the validation logic that does all the validation task. Okay. So for that reason, we need to have a whole change state manager. Similarly, now we have already created a change state manager object. We don't require the change state manager options, or basically the customizing options memory. So we'll just remove that. And then we have created a block directory, block data. This contains, I guess, 2 or 3 blocks. So we have that in terms of hexadecimal array. And then we are creating a block object through this raw block hexadecimal object. And after that, all of this stuff, we are destroying the block data, we are destroying the change state data, change state manager, we're destroying the context as well, because we don't need this. And since we have already done the verification here, so verification is done here with this method. So btck change state manager process block, which takes the chain main. Chain main contains the blocks directory. This block contains the block that you want to validate, and the new block is actually the status or something like that, like whether this block is a new block or this block. So it's like when you supply 2 blocks at once while doing full validation, it's like the block is already there. Now full validation, what it does, it's like whether that block is a duplicate or not. So you can't have 2 same blocks connected to each other. So for that reason, we need to pass a reference, or basically something to handle whether that block is a new block or not. So for that reason, we are passing a new block data here, or parameter here, and the result will contain, whether that result was successful or not. It will return just 0 and 1. So if you see here, if the processing of the block was successful. If it is 0, then that means the processing of the block was successful, and this will also return 0 for duplicate blocks, because like in consensus check, we are just performing whether the block is valid or not actually doing the full validation. We're just checking whether the block is valid or not. So for that reason, it will return 0. but it won't return invalid because that block is not invalid. The block is valid, but the block might be duplicate. That's what the difference is while doing the context free and the full validation. So how we get to know whether that block is duplicate and valid as well? So that's the reason why we pass here new block. So if new block is 0, that means the block is duplicate. If new block is 1, that means the block is, you know, it's like the new block and that is valid. So we'll handle that here. So if result is 0, that means the block is the block has passed the consensus check, and if it is new block, then that means the block is first seen. It is not duplicate block. If it returns 0, that means the block has passed the consensus check. But if the new block value is also 0, that means that the block is duplicate. It means that block is already present there. This is valid block, but this is already present there. So we don't want that block to be inside the data directory or to be connected with the blockchain data or the block data directory. So now if we run this command or run this code, then you can see here this is actually the notification. So this is what the notification does. It returns whether that block is valid. Yes, the block is valid. So if we didn't had any notification or the validation interface or notification interface callback, then we wouldn't have known whether the block is valid or not, or we might know the reason why the block was invalid. And also we won't be able to know whether what is the hash of the block, what is the type of the block, and what is the state of the block, and what is the current height of the block, what is the current header tip, and whether it contains the warning set or unset, and what is the block tip of the current blockchain. So if you see here, when we are passing the block again, first time this is the first the notification interface for the first block after the Genesis one. So this is all the notification we have got. And if you pass again if you pass another block, for example, yes. So if we again do make run, then that means that this block data has again been passed to the data directory, or basically the blockchain data you already had. So that means the block is valid, but it's duplicate. Here we have only seen the block once, so that's why the block is valid, as well as block has been processed. Block has been processed in the sense it is included in the blockchain or in the data directory. Now again, if you see here, this block is actually valid, but this is actually a duplicate block because we have already included the block in the blockchain or in our data directory. So that is the full validation. So you need a context for full validation, but for partial or just for the consensus check, you don't need a full validation. Basically, the context of the validation. So yeah, that was it for this session.